Hi, my name is Aditya and I am the CEO of Automaski. Today I am going to be talking about cracking AES cryptography with quantum computers. So one of the central pieces of cracking AES with quantum computers is something called the S box. Now what is an S box? It stands for substitution box. It is a lookup table used in the sub-byte step of AES. This lookup table maps 8-bit input to an 8-bit output. And this mapping is non-linear and invertible. It is based on mathematical function in finite fields, a Galois field of 2 to the power 8. And its design involves taking the multiplicative inverse in Galois field 2 to the power 8 and then applying an affine transformation. Now, the purpose is that it introduces a confusion and makes the relationship between ciphertext and encryption key complex. This provides resistance against linear and differential cryptanalysis. It also ensures non-linearity. So why is this S-box important in quantum AES cracking? When you try cracking, AES with quantum attacks, most of the attention focuses on Grover's algorithm, which provides a quadratic speedup. Now, however, the Grover's algorithm needs the entire AES encryption process to be modeled as a quantum circuit. And to run it, the entire AES algorithm has to be implemented as a quantum circuit and it has to be reversible. Now, the S box is the most complex and resource intensive part to implement in a quantum circuit due to its nonlinear nature and use of finite field inversion. Now, it is very difficult to make an efficient reversible logic design for the S box. Now, the S box is the bottleneck. It dominates the quantum resource cost, the number of gates, the qubit usage, and depth. Optimization of S box is the key to reducing total circuit complexity of the Grover's algorithm in attempting to crack AES algorithm. Now, various efforts have been made to implement the S box with various degrees of circuit efficiency. We are going to show you an example where we have three variants of the S box, and we are going to run them and show that what is their output vis-a-vis the classical output. So this is the regular, Qiskit circuit. We are defining the circuit in Qiskit, but instead of running it on IBM's quantum computers, we are running it on Automatsky quantum computers because Automatsky quantum computers can support thousands of logic gates and lakhs of thousands of qubits, logical qubits, and lakhs of gates. So this is the implementation of three circuits, but I will not go into them. That is the and this is the if you look at this is the S box lookup table, and which we are going to execute and try to crack. Now, this is how we are connecting to the Automaski's quantum backend. This is an IP address connected to our data center over a VPN. So it's a LAN IP address. You cannot access it from outside. We are going to run circuits, all the three circuits with 1,000 repetitions and take the top 20 samples of the histogram of results. So let's execute the first variant of the S-box implementation. The first S-box implementation is the most efficient. It uses 22 qubits and 371 gates. And as you can see, the classical result is 01010011. And if you see this in the reverse order, it is 01010011. And all thousands measurements have resulted in this sample. So this implementation is not only the most efficient, it is running on Automatsky's quantum computers, it is the most accurate and noteworthy. Now let's run the second S-box variant. This, the first one took 371 gates. This one takes 438 gates and 22 logical qubits. And this, you can see that the reverse, this answer is not correct. So this second variant is still, error prone, and all 1,000 measurements are of that, qubit combination. So the backend system is working extremely well. Just that the SBox circuit variant is error prone. Let us run the third variant. This variant takes 22 qubits and 809 gates. And let's see. So the classical result is 1000. And if you see the quantum result in the reverse order is the same. It's a 100% crack because uh, all 1,000 measurements resulted in this qubit combination. So it is exciting times for cryptography with quantum computing. Using quantum computers, you can crack RSA cryptography, elliptic curve cryptography, which secures Bitcoin, and you can also crack AES cryptography. I just showed you how you can implement the SBox, which is central to the AES Grover based cracking algorithms. And I hope you enjoyed the demonstration. Thank you very much. If you have any questions, please contact info@automatsky.com.